right, good morning everyone and welcome. Today it's back to business as usual again after the midterm exam and the Herkansing break and also those special lectures we had last week. So we're now continuing exactly where we left off before that phase with the graphics pipeline. But because it has been quite some time since last time, I will start with a little recap or to refresh our memories of what we did last time because we are immediately continuing there. So last time we talked about the perspective projection, which is the process of creating a perspectively correct image of our 3D model on our 2D screen. And we saw that we can do this all with matrix multiplication in some sort of pipeline, like the graphics pipeline. And it's called a pipeline because we have a sequence of steps, and each step, the output of one step is always the input for the next step. That's why we call it a pipeline. And if we look at all these steps, we first have to start by specifying the view frustum and the camera position, so our viewing parameters. So we place a camera somewhere in our scene and then we direct it where we want to look at. And that way we also see, because the camera has a limited field of view, of course, we define a so-called view frustum, which contains all the objects we want to draw. Then we said to make this drawing easier, we move from world space to camera space. So the camera is at the origin, which makes our calculation obviously easier. And also we said that we distinguish with projection between perspective projection and orthographic projection, where orthographic projection is just a projection towards one of the axes, which means it is much easier because if we project in the direction of one of the axes, we can basically just ignore the coordinate from that direction, and then we already have our 2D image, so we don't need to do any calculation. And to benefit from this easy way of projecting, we said we do not do a perspective projection by calculating it directly, but we transfer our view, we modify our view volume in a way that we can do an orthographic projection. That is, we move it from a view frustum to a so-called orthographic view volume, which is an axis parallel box. And because it's an axis parallel box, and during the transformation we preserve all the sizes and relative positions of the objects, we can then just do an orthographic projection. But before we do that, we make another simplification step, which is going from the orthographic view volume to the canonical view volume, which is just a normalization basically of having the values between -1 and 1 around the center of our coordinate system. And then in the last step we do the windowing transformation, which are actually two steps. The first is the orthographic projection, which I said is just very simple. We just remove the third coordinate, and then we're still in this normalized window of -1 to 1, so we have to map it then to the window that we have on our screen or to the size of our screen by a windowing transformation, which is then just a simple scaling transformation. So again, we can do this with a simple matrix multiplication. All of these steps can be done, we've seen, with a matrix multiplication. The only part where we had a problem with our existing matrix framework at that time was when we went to the orthographic view volume, and then we saw that this doesn't work with the matrix multiplication how we have learned it by then. So we needed to extend this framework, and that was the most complicated step in here, which is why I'm continuing here, or also repeating a little bit. At the beginning we said we used matrices for linear transformations of vectors. So for example, if we have a vector x, y, z, we can multiply it with the matrix, and then, for example, for the first coordinate we get a value like this, where we say the x dash, the transformed x value, is ax plus by plus cz, and the abc's are of course the first row of our transformation matrix. Likewise, we get it for y and for z, then we multiply it with the coefficients in the second and the third row of the matrix. And we've seen then, we learned then that by choosing these A, B, and C values appropriately, we can do all kinds of transformations. So for example, we have seen if we set A to 0, A to 2, B to 0, and Z to 0, we can do a scaling of the X value by a factor of 2. Or because we also have the other coefficients here in this equation here, we can, for example, use A0, B1, and Z is 0. That results in copying the y value to the x value, and we used that, for example, when we made this reflection matrices where we just needed to swap, for example, the x and the y value. So we copied the y value into the x value, and for the second row of the matrix we had then 1 0 0, which means we copy the x value in the position of the y value. So we just swap these by doing choosing the matrix appropriately. So we've seen we can do all kinds of different transformation with this by choosing the matrices in a clever way, and we also learned how to choose them to achieve a certain transformation. But we've also seen that when we want to do a translation, we cannot do this with matrix multiplication, because for a translation, which means we want to move, for example, the x coordinate by a fixed value d, we see we cannot achieve that because all the values here always depend on this parameter here. The only way we can eliminate this parameter here is by setting, of course, the coefficient to 0, but then we cannot add a constant value because then everything is gone. So there is no way how we can choose the ABCs that we can achieve this translation here, or that we can achieve a coefficient in that way with a constant factor d. And this is why we extended our framework to the homogeneous coordinates, which was basically that we said instead of 3D, we just go one dimension higher by adding another row to our matrices and also another column, which is now, I should probably call this dx here to distinguish between the other d's, dy and dz. And by doing this, we can achieve this kind of transformation of our x value, which is then, if we choose the values appropriately, so for example, if we choose a, b, c 0 and d some value, I don't know, 2, then we can of course make something like x plus 2, which is impossible to do with the traditional linear transformation. But of course we also see we have an additional row here now, so we have to represent our points differently, and if we do this by setting a value 1 here, then we see that we can also do all the other linear transformations with this. So if we, for example, set d to 0 and again set here 2 0 0, or the other example we had was 0 1 0 0, then we can do all these transformations that we had here as well with this extended framework. So we see it all fits into each other, and we can this way do the transformation. We just have do also the translation. We just have to represent the point a little differently, and when we draw it, of course, we only draw the first 3 coordinates and ignore the 4th one. So we can see, we can arithmetically look at this and see that this works out, but it's also, for some people, it's always helpful to have a geometric interpretation of it. And if you remember how we motivated this from the geometric interpretation, this is for the 2D case. Of course, I cannot draw the 3D case because then we had to go to 4D, which is something I cannot draw. But for the 2D case, we had here a value, for example, a point xy, and then we said we're just moving this, we're just adding a 3rd dimension by representing the point with xy1, and that point is then of course xy0, and then we can do a transformation that moves this point by a fixed value here. So this is our dx, and then we have here a point x plus dx y1. And then we say, okay, now we have done our transformation. Now we go back to this original 2D space, which is then x plus dx y, and then we just ignore the 3rd coordinate, and then we have exactly achieved what we wanted to achieve with matrix multiplication, which we couldn't do if we would have stayed in 2D. So we're basically moving in this set equals 1 plane and then do all our operations there. And because we have this 1 value in the 3rd coordinate and the last row with 0 0 0 1, we can do all the other transformations there, and it doesn't influence our result. In the end, we just have to ignore the 3rd coordinate, or the last coordinate, which is the homogeneous coordinate. But then we went on when we did the perspective projection, that we realized we need a transformation of the coordinates now in a way that gives us this xs is was defined as dx divided by z, and the ys that we needed was the y divided by z, Actually, I should choose dv here. Should name it differently because we also have a parameter d here, and that is of course a different one. The dv here is the distance to the viewing plane. That's why we have chosen at that time the same letter, but of course if we have d used here somewhere else, we have to name it differently. So we've seen here we need to have an operation that allows us to divide by a coefficient, and we cannot do this. Of course we can choose here coefficients that divide by something, but only by a fixed value. There is no way we can choose the ABCDs here in a way that we divide one coefficient by another coefficient. So we have to again extend our framework in a certain way, and we did this by saying, well, let's just use this last row of the coefficients in a way that we extend it in a way that we do not only allow 0, 0, 1 in the last row of the matrix, but we allow all different values. So we have E, F, G, and H here in the lower row, and that means if we multiply then with this point here, we can get this kind of transformation, which of course if we choose the values appropriately allows us to create this kind of values. So for example, if we choose A is dv, and we choose B, C, D, E, and F, and H as 0, and we choose G as 1, then we can achieve exactly this here. Let's call it I. Then I don't have to write it again. Here we go. So obviously we can achieve that, but also we see that if we choose these letters correctly, these coefficient, the values for these coefficients cleverly. For example, if we choose E, F, G as 0 and H as 1, then we have again an affine transformation. So we have all things that we can achieve here, we can also achieve with this one. So from the calculation, this works. The only problem is, of course, if we choose these values not to be 0s and 1, then we get different values here, and we also get different values here. But if you look at it arithmetically, you see that these values here are just the original values divided by multiplied by this w value, which is why if we go back, we have to divide them by this w. So if we represent a point like this, we have to, this point here then represents this point here, which in turn then of course represents, like here, the original point x, y, z, but only now we have x is x tilde divided by w. So before we draw it, we do not just have to remove this 1 here, the last coefficient, but we first have to make sure that there is a 1 there and that all these values here are appropriate. And that means we have to divide by the last coefficient. Now you can do this arithmetically, and then you will see that this actually works out in all cases. But like in the other case, it is also, there is one way to think about it geometrically, which I've drawn down here. I've drawn it here only in 1D because that's much easier to draw, but of course the generalization to 2D is straightforward. And the generalization again to 3D is also straightforward, but I cannot draw it anymore. So here on the left side we have the affine transformation. That's basically the 2D equivalent of this image that I just showed you here, where we say we have here, we map a point x to a point x plus d by doing a linear transformation from x1 to x plus d1. And of course this here is a shearing, so we can do this transformation with matrix multiplication, whereas this here we cannot do, which is why we have chosen this way with the homogeneous coordinates. Now here on the right side we have the perspective transformation, where we now say the point x is not necessarily represented by x1, but it is represented by x tilde divided by W1. Yeah, W1, because we can also choose different W's. Yeah, and this x tilde is, here we have it, here is W times x. And then we see, of course, if this W is 1, we have the same as here. So we are basically moving everything in this level 1, or in the plane set equals 1. But if this W has another value, which can happen because we multiplied with that matrix that has these different coefficients in the bottom row, then we end up at another point here. But since we are multiplying also the x value with it, we end up at a point somewhere here on this line. So all the points on one line here represent this line here. So not only this point here represents this x value, but also this point here represents this x value. Now you see why I have, actually that is, what did I write here? That's nonsense. It's x tilde w1. That's the point. We're moving in 2D, so it's, the division doesn't make sense. Yeah, so you see here, and of course I have written here x tilde, of course, the same, but this x tilde is now w2 times x, so you see this is a different x value, which is further down here, but also it is higher up, so all the points here are on this line. So, and then we can do our transformation here also. So instead of doing the translation here, we do the translation here at the top, but like you remember, for shearing, the higher we're up, the more we are pushing it to the side. So we're moving further to the side here. So if we would here now, so here we get then this x tilde. I did it again. Why didn't you protest? Here, so x tilde plus d we get here, and w2. Now, of course, if we, like in this case, just ignore the third coordinate, we end up at a very different point here. But that is why we do this step of so-called homogeneization, where we divide by w2, and then we get here x tilde plus d divided by w2. Now there is a divided, and then the third coordinate is a 1. That was badly drawn here. That's this point here. And then, of course, we can just remove the 1 here, and then we end up here at the very same position as we would have ended up here. So you see here, it kind of also from a geometric, if you have the image in your head, it also becomes clear why this all fits into each other. And although we have values that are totally different than before, it's kind of because you're just doing the operations in a different level, and you also might switch the levels in between, because when you multiply with a matrix, you get a different w value, but it doesn't matter, because in the end you divide all the coefficients through this w value, which basically means you're moving along this line, and then at the end you go back to the level of 1, and then you do the projection down into the ground plane, which is then your 2D value, in this case the 1D value. Good. So yeah, so this is just a summarization of it. So you see here we have the matrix now. Instead of 0, 0, 1, we have these coefficients here. This at the beginning is still the 1 value, but then of course we see when we do the multiplication we have a different value here, which is why we have to do this homogeneization step, which again gives us then the 1 value here, and this is then our x tilde divided by the w. And then we've seen if we choose these values appropriately from the matrix, we can actually create a division of one coordinate, one coefficient, one parameter by another parameter, so x divided by z, for example, here when we choose the coefficients of the matrix appropriately. Another thing we see if we look at it in this representation is if we multiply the matrix with the coefficient, with a scalar value or a constant value, we get of course different values here, but all the coefficients are multiplied with this value, which is why when we do the homogeneization, this here is going away, and we get the very same result as we get it here. Now from a geometric point of view, this also makes sense, because it basically just means we do the operations in a different level. And one consequence of this is, someone realized this last year, that in the second edition of the book, they're actually using a different perspective matrix. So if some of you are using still the second edition and not the new third edition of the book, you might have been surprised that they use this. So this is the second, and this is in the third edition of the book, that they use this transformation matrix. But you see here, this is just here multiplied with 1 divided by n, or multiplied by n. So this is just a scalar multiplication of it. And so we achieve the very same results. We're just doing our operations in a different level. But this is also why there is a mistake in some later calculations in the book in the third edition, which actually was found by one of your colleagues last year. And then I mailed it to the author, so it is in the list of erratas of the book. So make sure to check that list of erratas that is on the book website, because there is one mistake where they basically copied the previous edition, the equation from the previous year edition, but forgot to update this one matrix because they didn't remember that they use a different matrix now in the book, in a new edition. Good. All right, so much about the perspective projection. Now, when we did this, we made 3 simplifications. We said, first of all, we assume that all our objects, all our triangles, are within the view frustum. Secondly, we said that we assume that they do not overlap each other. And third, we said that we are only projecting grid models. So we are only looking at the edges, which means we are only looking at points, at single points, and not at the whole objects. So these are the 3 things that we still need to address to get this all full covered and be able to do everything. One is we have to deal with situations where triangles are completely outside or partly outside of the view frustum. So for example, this case here, and also this case here where the triangle is partly within the view frustum. This is a special case and we have to treat it specially. And we have to deal with situations where triangles are overlapping each other. So if we have a situation like this here, of course, we don't draw the full second triangle, so we have to take care of that as well. And of course, we do not only want to have grid models, but we want to have the models shaded in textures. And we already learned a little bit about texturing, but we will talk a little bit more about this in relation to the graphics pipeline. But today we will focus on these 2 issues here. Or actually, there are 3 issues. One is the front-facing thing, the other is the clipping, is the partly intersection, and the other is the that the triangle is completely outside of it. And this partly intersection, so the triangle is completely outside of it. Some of you might already know this if you started with the third practical, because that is one of the exercises. Then we use a procedure called culling, and we'll talk about this later. First, we'll start with this situation here where the triangle is partly inside of the view frustum, and then we use an approach called clipping. And what we do in this situation is, first of all, of course, we have to check, does the triangle is this one of the triangles that is partly inside of the view frustum or partly out of the view frustum? So we have to verify if the triangle intersects with the hyperplanes that create the view frustum. And then, of course, if it does, we have to process it or deal with it, which basically means we have to create a new triangle. So let's just draw it in 2D. If you, for example, if this is one plane of your view frustum and this is your triangle that is partly outside, then of course you have to first of all find this triangle, and then you see, okay, it intersects at these 2 points here. That means we have to cut off this part and create a new triangle that has as vertices now these 2 intersection points of the triangle with the hyperplane. Good. So, and to do this, we have to remember what we learned at the very beginning, which is the implicit representation of a plane. Because if we do that, then we can calculate these intersection points quite easily. And fortunately, I've seen when correcting the exams that a lot of you, or most of you, actually know this. So that was quite good. But nevertheless, it's always good to refresh our memory. So the implicit equation of a plane is defined by a normal vector of the plane and a vector pointing to a position on the plane. So a vector P0 and a normal vector. And then if we say if a point minus this point on the plane is a scalar product with the normal vector is 0, then the point is on the plane, which makes sense, of course, because the point minus p0 is a vector on the plane. And if that is the scalar product with the normal vector is 0, then it means they have a right angle, which means it is on the plane. Good. And we can also write this differently by doing actually the scalar product, and this is just a different way to write it, which makes then the calculation easier later. We have also seen in the and this is a way to verify if a point is on the plane by saying it is on the plane if this equation equals 0. So for all points that are on this plane, we have f of p equals 0. And in one of the earlier tutorials, in the first or in the second one, we also have seen that this equation splits our space into a positive and a negative subspace, which means that all points on one side of the plane, if we enter them in the equation, will end up with a positive value, and all points on the other side end up with a negative value. So for all points here, we have f of p is larger than 0, and for all points here, we have f of p is smaller than 0. Now, why did I write it that way? Why didn't I write it the other way? Why didn't I write here smaller than 0 and here larger than 0? And the reason we also know that the reason for this is that we already learned that also in the tutorial, which is that the normal always points to the positive side of the plane, to the positive subspace. So if the normal points up here, then this must be, all values here must be larger than 0. And this means if we create our view frustum in a way that the normals of the planes representing those sides of the view frustum always point to the outside, that means that all the values here are larger 0 and all the values here are lower 0. And that means if we have, for example, here a triangle, we can test if a triangle intersects by just checking on which side of a plane these points are. Because if they are on the same side of the plane, they do not intersect with the plane, or the segment between them doesn't intersect with the planes, obviously. So for example, here we have L of P equals 0, but here we have L is smaller 0, and here we have L is larger 0. And we also see here that there is a mistake here. I didn't find the source file for this image, which is why I couldn't correct it. But we see here for the point A and for the point B, this value is both 0 because they are on a different side of the because they are in a negative subspace. So we just have to enter these points in the equation, and we can immediately see that they do not intersect with the line L. But we also see that they intersect with the line F because with the plane F, because if we enter them in a plane equation, we get a negative value for A and a positive value for B, which means they're on different sides, which means, of course, that the segment between them intersects with them. So we see that this is a very easy way to check if a triangle segment intersects with a plane equation, with a plane. And now, when we know this, then we want to create a new triangle. Yeah, the question? You mean like a case like this? Ah, case like this. Let me think. But you have an intersection here. For this line, you get a negative test, a positive intersection test. Because with this line, this segment intersects and this segment intersects. And then, of course, I mean, you could also have this situation, and then you have a test. But we'll talk about how to do this then later. Yeah, good. Okay, yeah, but it's good that you ask, because you always have to think about these special cases when you do these algorithms. Good, yeah, so if we know that it intersects, then we have to calculate the intersection point. And this is why I did this transformation with the line equation here, because if we represent it that way, and then represent the intersection point in the parametric, this segment by the line here, so this is the line P of t in parametric form, then we can just put this into the plane equation and do a transformation, and then we get this t value t dash, and this t value t dash then represents exactly the t value for this point, for this intersection point b dash. So b dash is this line equation at the position p t dash, and then we have our intersection point, and then we calculate the next intersection point here, and then we can create our new triangle. Now, of course, this is an easy case, and you already talked about a more complicated case. I mean, the first most straightforward case is that we say, well, this point C here does not have to lie outside of it, but it can also lie inside of it. And then that's this case here, and then we just have to create two triangles out of it. And likewise, if we have an intersection like this, we just cut it off here, then we have two triangles here, then we cut it off here, and then we have to create two triangles here, and then we have our three new triangles. And that, I think, also answers your question here, what we do here. We get an intersection here, because we are on different sides of the plane. Then we cut it off, for example, here, then we have a triangle, then we cut it off here, and then we have another triangle, and then we have our new triangle here. So that works quite well. In this case, for example, we need to do more cutting, so we cut it off here, and then we create, for example, we have this here, so we can create a triangle here. Then let's say we cut it off here, then we see here this is not a triangle, so we have to, for example, can do it like this to create two triangles, and then we cut it off here, and then we see these two are both not triangles, so we have to cut them off again. But we also see that this cutting off, the way to do is not unique. So for example, the last case where we had this part here, I cut it off here, but I could have also done it in that way and create two triangles here. So it is not unique, but I can always cut it down to have triangles. Good. So we know now how to do the clipping, but an interesting question is also when should we do the clipping? For example, if you have read the practicals already, the practical assignment, there is a quote here, I wrote it down so I don't make a mistake. For the culling, the quote says, "The earlier you can remove triangles from the rendering process, the better it is for your application's performance." Which seems straightforward, because if you don't have the triangle, you don't need to process it, which should make the performance better. But of course, we also have to consider the process of cutting them off. If that process is easier or more efficient to do at a later stage, we have this trade-off between, if we get rid of the triangles earlier, we don't have to process them. But if this getting rid of takes so much time, is much faster if we do it later, it might be better to do it later. Now for the culling, there is a different approach to do it, but for the clipping, this cutting off the triangles, as we've seen with these algorithms, can involve a lot of calculations, which is why it's worth thinking about what is the best way, or where is the best position to do it. Because if we do it here, for example, we have to calculate this cutting with this hyperplane, which is a little more complicated than this hyperplane here, because this is an axis parallel box, so the hyperplanes here are actually quite easy. So for example, here this is the first, let's look at the, so these are the hyperplanes for the orthographic view volume. So if you look at it here, for example, the first one, if we look at our 3D coordinate system, X, Y, and Z pointing out of the screen, then we have this axis parallel box with L to the left, R to the right, and then of course we see that this plane here is all points, or every point is on this plane if the minus x, the x value minus x is the same as the L value, or if minus x plus L equals 0, then of course the point is on this plane no matter what the z and the y value is. So this is should be pretty clear that these are the equations for this orthographic view volume, for this box here. And of course it should also be clear that the calculation with this planes is much easier than with the more complex plane, the more complex hyperplane here. So if we do it later, we actually can calculate the intersection much more efficiently. Problem with this is we run into one problem if we have objects that are behind us. Now you remember last time when we talked about the perspective transformation, we said that the set value is not directly preserved, we only preserve the order of the set value. And we said that this is the only thing that we need, because we only need the set value to determine in which order we are drawing the triangle. So if the triangle is closer to us, we want to draw it on top. And that means we only need the order of the set value, but because we're not drawing in that direction, we don't need the actual value. And then we made a proof that our transformation matrix actually keeps the set values on the near plane. On the near plane, it keeps the set values on the far plane. On the far plane, and in between, it preserves the order. So we made a long proof to show that. But that was under the assumption, of course, that all the objects are within the view frustum. And now we're doing the clipping. That means we also have to deal with situations where parts of the object are outside of the view frustum. In particular, we have situations where parts of the object could be behind the eye. And if you look at this function here, we already drawn it last time. The new set value is proportional to minus 1 divided by set. So n and f are constant values, so the only parameter here is the set. So if we look at a function proportional to 1 divided by set, that's like this, or to proportional to minus 1 divided by set, that's like this. And yeah, and so you see here, if the image looks a little bit complicated. I hope you can read it, but it's I copied it from the book. It's actually, if you look at it, what it represents, then it becomes quite clear. So this is our function here. This is the set value. This is the set dash value. And if we now this is here, the set dash is at the position, or 0 is our offset, is our I position. To that side we have a set smaller than 0. To that side we have a set larger than 0. And we see here, if we are within, if we are within, this is the near plane and this is the far plane, within that range the set value is mapped to a new set value that fulfills all these conditions that we have proven last time. But if we go beyond the I in the negative area, then we switch to this upper part of the function, and that means also we're switching the sign from negative to positive, which means that a point that is behind the eye, now after the transformation, is suddenly in front of the eye. In that case, it's even behind the far plane. So we get a triangle that is not the same as the original triangle in our model. So we get a problem here, which is why we cannot do the clipping after the perspective divide, and which is, by the way, also the motivation why we, in any case, we have to do a clipping. Because some people always ask, yeah, why do I not just calculate them and then not draw them, because they're just not on the screen. But you get the calculation, you might get the calculation wrong if you have cases like this when you do the perspective projection, if you do not cut off these parts before you do that. So we have to do the cutting off before, and we can do it quite easily by or the way to do it is relatively simple. It's just using the inverse transformation to get the corners of this view frustum, and with the corners we can also get the planes, and then we can just calculate the intersection. So the steps to do there are quite straightforward and quite easy, but of course they are less efficient than if we would do it with the other plane equations, because these plane equations are usually much more complicated, so they require more calculation time, so they are less efficient. The good thing is that there is actually a third option to do it, which is in between and takes basically the best of both worlds, which is do the clipping just before the homogeneous divide. So we do the clipping in homogeneous coordinates, that is, we do it here after we have done this transformation to the orthographic view volume, but before we do this homogeneous divide, because this homogeneous divide, this dividing by the set value, is exactly what causes here this problem that it switches here to from negative to positive. So by doing it before, we avoid that, but we still have very simple and easy equations to do that. And these equations are, if you compare this with the original one, so for example the first one, the first equation was oh wait, I have it here. Yeah, this is easier to understand. So these are the equations after the perspective projection of the hyperplanes of the view frustum, after the perspective projection, but before the homogeneous divide. After the homogeneous divide, it was x, let's call this now, because we have different values here, x2 dash, y2 dash, z2 dash 1. So we have here x2 dash equals x dash divided by w dash. So this is the homogeneous divide. And then we see that the plane equation afterwards is x2 dash l plus l equals 0. So that is exactly this equation that we had here, only because we have transformed the coordinates now we have to write x2 dash. Now if we put this here, let's call it I, into it and do multiply it with L, then we see that this is exactly this equation here. So you see this is indeed the hyperplane of the orthographic view volume, but before the homogeneous divide, that is in homogeneous coordinates. So we have a simple plane equation to do the clipping, but still we do not run into this problem that we had if we would do it at the very end. Good. So yeah. The next step takes a little longer, which is why I think we should make an earlier break here. So let's meet 5 minutes before 10 and have a break now.